Good morning, students. Am I audible in both classes? Can you people type it in the chat? Is the presentation is visible in both classes?
Yes,
Yes?
sir.
Okay, fine. Thank you. Due to some network issue, Marian was not able to present today. Okay. Probably after completion of this particular session, if time permits, he will present. Otherwise, we will continue in the next session. Okay. Fine. Before getting into today's topic, these are the things we have discussed in the previous session. Okay, so we have discussed about some sample instructions machine cycle and the timing, how much T state it take for execution. Fine. Then we have discussed about software delay. Okay, can you people type it in the chat? Who is going to generate the software delay? Yes. To generate this particular timing, whether the microprocessor is going to execute some program or we are using some other hardware in the case of software delay. Yes, very good, Anthony Surya. A dummy loop. Okay, so a loop is repeatedly running with a finite count value. Okay, it should not be infinite. If it is infinite, it will keep on executing the loop. Fine. So a finite count with a finite count value, we are executing a dummy loop which is going to generate the, that means the CPU is going to generate the timing, fine, the delay, fine. Then we have discussed how to calculate the delay of a delay routine, fine. Then we have introduced interrupts, fine. So before getting into the interrupt, previous class I have asked you a few questions, okay. So I will show you the answer for those questions, okay. So DADB instruction, it's a 1 byte instruction, okay, but it involves 3 machine cycle. Fine. The reasons are mentioned here. Kindly take a screenshot. Actually, it fetches the opcode after it decode the opcode during the first machine cycle. That means opcode fetch. At a T4 state of opcode fetch, it knows what operation it has to do. Correct? The CPU know what operation it has to do. Fine. As it is a 16-bit addition, okay, it takes some time to execute. Even though the operands are internal, as it is 16-bit addition, it takes some time, okay, so that the operation can be completed. Fine. During that particular time, the buses of 8085 will be idle. That we call it as bus idle machine cycle. Okay, like opcode fetch, memory read, memory write, IO read, IO write. We have one more machine cycle called bus idle machine cycle. Okay, so during that bus idle machine cycle, some of the internal operation takes place, whereas the bus will get idle. That's why it is called as bus idle machine cycle. Fine. So during one bus idle machine cycle, the lower byte of addition can happen. During the second bus idle cycle, the higher byte of addition can happen. Fine. So totally it takes 3 machine cycle. Fine. So it takes 10 T state. Fine. Then the next instruction INXH. So here it is 1 byte instruction only. So only opcode fetch. What about the duration of opcode fetch typically? Can you people type it in the chat? What is the duration of? Yes, very good, 4 T state. But here, after decoding, it has to do a 16-bit operation, correct? Here the instruction is INX. INX means 16-bit operation. To perform the particular operation, it takes extra 2 T state. That's all. Okay, please remember one thing. Some of the instruction takes 6 T state for opcode fetch. Okay, not all the instruction, some of the instruction. Okay, some of the instruction requires 2 more T state for opcode fetch machine cycle. Fine. In the case of INXH, it takes 6 T state. Okay, the 2 T states are for doing the 16-bit operation. Fine. If the operation done by the CPU is 16-bit, it takes some more time, even though the operands are internal. Fine. In the case of addition, okay, it takes 2 bus idle cycle, whereas in the case of INXH, it takes only 2 extra T state. Fine. It doesn't need any extra machine cycle. Fine. Then NOP instruction, it is 1 byte instruction. Okay, so opcode fetch machine cycle, so the number of t state is 4t. Okay, in the case of halt, I think here wrongly typed as 7t, sorry, so it is 5t only. Fine. In the case of halt instruction, after opcode fetch, okay, at the end of the opcode fetch machine cycle, that means at T4, after decoding, the processor know it has to stop the further execution of the program, correct? So the next cycle will be bus idle cycle for 1 T state, that's all. Fine. After that, the processor is not going to access any external content. That means it is not going to fetch the program anymore. Fine. After halt instruction, what we have to do? After execution of the halt instruction by the CPU, fine, what we have to do? To get the CPU to normal working, what we have to do? நம்ம lab programல execute பண்ணோம், கரெக்ட்டுங்களா? கடைசி instruction halt instruction தான் யூஸ் பண்ணிருக்கோம். Fine? Yes, very good. We have to reset the microprocessor. Fine? Clear? So that's the only way you can come out from halt. Fine. So then few more instruction I have mentioned here. PCHL, it takes 2 extra T state, that means 6 T state for opcode fetch. SPHL, it requires 6 T state, fine, for opcode fetch. Fine, just note down these things. So push B, okay, here opcode fetch we know, memory rate, that means we have to push the content of B register into the stack, then C register into the stack. But during the opcode fetch, it takes extra 2 T state for what? To point an empty location, it has to pre-decrement the stack pointer, correct? So for that, it takes extra 2 T state. Whereas in the case of pop, it is post increment. Fine, post increment abin solrappo namakku extra T state thevapadaadu. Kindly note down these things. Okay, so next I will move to unconditional branch instruction. Fine. So last class sollindom jump, call, return. Idu moodhukku ethana machine cycle varum. Fine. So here it is, sorry. Sorry, I think there is some mistake. Fine. Okay. Fine. So now you people can take a screenshot. Fine. The case of jump operation, we have the opcode C3. So the first machine cycle is opcode fetch. Then the memory address has to be read by the CPU, so that it takes 2 machine cycle, 2 memory read machine cycles, so that it can read the lower byte then higher byte. Fine. So after it fetch the instruction, whole instruction, it know it has to be placed in, that address must be placed in program counter. Fine. So that's all about the jump instruction. What about in the case of call instruction? What about in the case of call instruction? Before getting into that particular address, what it has to do? What is the difference between jump and call? Before getting into the address we mentioned, what will be done by the call instruction? Whenever call instruction got executed, the CPU do what? Kindly type it in the chat. Yes? Yes, very good, Sajid. Storing the return address in the stack. Very good. In classroom 2, Sajid typed. Very good. It stores the return address in the stack, correct? So during call instruction, after opcode fetch, it has to pre-decrement the stack pointer so that it can put the lower byte of the return address, correct? See, during the opcode fetch itself, it is doing the pre-decrement of stack pointer so that it point to the top of the stack. Fine. The next memory reads are used to get the get the address for what we have to transfer the program execution. Call 9000. CD is the opcode. So the first machine cycle is opcode fetch. the second machine cycle memory read and third machine cycle memory read are used to get the address to which we have to call, correct? Or the program from which address we have to call. Fine. That information is taken. After it takes those information, it stores the program counter value, higher byte into the stack, then lower byte into the stack. Clear? Fine. So this is the thing, sequence of things happen in the execution of call instruction. So it requires 5 machine cycle, 1 opcode fetch with 6 T state, not 4 T state, it is 6 T state. Fine. Then 4 extra cycles, 2 memory read cycle and 2 memory write cycle. The 2 memory read cycle are to read the address in which the subroutine is available. Fine. It takes another 2 extra machine cycle, memory write machine cycle, to store the next instruction address into the stack. Fine. So that's why it takes 5 machine cycle. Okay. Similarly, in the case of return, we are not mentioning any address. So by single opcode fetch cycle, it can know what it has to do. Fine. From the stack, it is taking the value and putting in program counter. Fine. Popping out the stack data. That means the last 2 bytes what we pushed is a return address that is getting into the program counter. Fine. So opcode fetch. So after decoding, it do 1 memory read cycle to get the return address to lower byte of PCL. Then another memory read cycle to get the higher byte of the address into the PCH register. Sorry, is it clear? Is it clear? Yes. See, branch instruction porappa jump அப்படின்னு சொன்னோம்னா return address store பண்ண தேவையில்லை, correct? So opcode fetch, read the address and put it in program counter. That's it. Whereas in the case of call and return, it involves with the return address, correct? During the call instruction, after fetching the instruction, after the 3 machine cycle, it need 2 more machine cycle to put the return address into the stack. Okay, that's why 2 memory write cycles are involved here. Fine. Whereas in the case of return, after opcode fetch, wait a minute, here it is 3, it is not 5, sorry. Sorry, I'm sorry. Here it is 3. Fine. So during the return instruction execution, the first machine cycle is opcode fetch. Okay. Then 2 memory read cycles are involved to get the return address into the program counter. That's it. Okay. Next. So in the case of conditional branch instruction, please listen. If the condition is true, it executes as like in the previous thing. Okay. If it is false condition, okay, it will skip from the machine cycle 2 after the machine cycle 2. Fine. If the condition is false, then it won't continue. Okay. See, first it will do the opcode fetch C2, then it will read the lower byte of the address. During the time itself, it will check the condition. Fine. If the condition is false, it won't fetch the higher byte of the address. It will just skip this instruction and go to the next instruction address. Similarly, in the case of call and return. Clear? During the false condition, it will skip the instruction. Okay. Once it decoded, after it find the status of the flag, it will stop fetching the instruction further. That's it. Okay. Kindly take down this. If it is true condition, this thing happen. If it is false condition, these things will happen. Fine. This and all for your reference only. Okay. If you have any doubt, you can contact. Okay. Now we will get into the interrupts. So in the previous session, we have given a brief introduction about interrupt. Okay. We'll go with few definitions. So what is an interrupt first of all? Can you people type it in the chat? Who is going to initiate the interrupt? Whether the CPU or IO device. Yes, very good. Request from IO device to CPU. Very good. So So request from an IO device to CPU to get a service. Okay. So interrupt is initiated by the IO device only. It is asynchronous in nature. That means at any point of time it can occur. Then what is meant by vector address? What is meant by vector address? Once the CPU acknowledge an interrupt, okay, the particular address will be there. From there only the service program will start running. Yes, very good. What Anthony Surya typed is address where ISR is stored. Very good. See, interrupt service routine will be there. Find that particular address for each interrupt. We call it as vector address. After an interrupt is acknowledged by the CPU, the program is vectored to a specific address. Okay. In that address, we will be having a program that we call it as interrupt service routine. Okay. And the address of the program pair interrupt service routine. Fine. Then we have priority queue. When more than one interrupt occurs, there is an order of priority. Based on that only, the interrupt will be serviced. Fine. So these are the things we must know before getting into the interrupt processing sequence. Okay. So now we will know how the interrupt will be handled by the microprocessor. Okay, 8085 microprocessor. Fine. Okay. Now you consider this is the main program. It's a memory locations arranging in order. Okay. Here we will be having the main program. Okay. Fine. So here we will be having the ISR routine. You consider these two things first. Okay. So this is our main program. So this is our ISR routine in memory locations. Clear? Fine. Now you consider the main program is getting executed. Correct? So at this point of time, interrupt comes. At this point of time, the interrupt occurs. Fine. What the CPU will do is it will complete the current executing instruction first. Or instruction execute agarappa enak interrupt vanduchu appadina what the CPU will do is it will complete the execution of the current instruction. Okay. Yes, is it clear? Is it clear or not? First we are considering the main program is getting executed. At any point of time interrupt comes, it will complete the execution of the current instruction. Fine. After that what it is doing? It is sending interrupt acknowledge. Okay, if it is INTR interrupt, it will send the interrupt acknowledge through INTA bar pin. Fine. So after that, what it is doing? After acknowledging the interrupt, what CPU is doing? Once interrupt occur on odane, it has to go to the ISR routine. Correct? It has to execute the ISR routine. Before that, what it is doing? Any idea? After acknowledging, it is saving the program counter address into the stack. Why? Why? What is the reason behind that? See, once the main program is running, once interrupt occur, it will finish the execution of the current instruction. Okay, then it acknowledge the device which interrupt. Correct? In the device on the interrupt panicho, it will acknowledge to the device. Okay. After that, it is saving the program counter address, correct, into the stack. Fine. Then it disable further interrupts. What it mean? What it mean? It's very, very important. What it means? It disable further interrupts. What it means? Or interrupt service start பண்றதுக்கு முன்னாடி what it is doing? See, when this particular interrupt program is running, அந்த டைம்ல இன்னொரு interrupt வந்தா என்ன ஆகும்? That will get recognized by the CPU. Fine. To avoid that, the internal hardware, what it is doing is, it save the program counter value into the stack, then it disable further interrupts and go to the interrupt service routine. Clear? So the steps are konja note panikonga. When interrupt occur, the first step is the CPU complete the execution of current instruction, then it acknowledge the interrupting device. Okay. Then it save the return address into the program counter, return address available in the program counter into the stack. Then it disable the further interrupts. Once an interrupt is acknowledged by the CPU, it disable further interrupts. Okay. The programmer has to write some instruction to enable the interrupt again. Fine. So it is getting into the service routine now. Interrupt service routine poyachi. Fine. At the end of interrupt service routine, what we have written? Can you people type it in the chat? Run the instruction in the service program. Yes. What are the two instructions? What are the two instructions we have written? Whenever we call a particular function or a subroutine, definitely return must be used. Correct? So RET instruction எழுதிருக்கும். அதுக்கு முன்னாடி ஒரு instruction எழுதிருக்கும். What is that instruction? What is that instruction? Mission control instruction படிச்சோம் இல்லைங்களா? ஒரு 6 instruction படிச்சோம். EI, DI, SIM, RIM, NOP, HLT. Correct? In that, EI is one of the instruction. Correct? Yes, very good. Enable interrupt. EI stands for enable interrupt. This is the instruction to enable the interrupts. Clear? So please note down one thing. In 8085 microprocessor, whenever interrupt is acknowledged, whenever an interrupt is acknowledged, it stores the return address into the stack, then disable further interrupts, then it go to the ISR. Fine? So the programmer has to enable the interrupt at any point of time in the ISR routine. எங்க வேணாலும் நம்ம enable பண்ணிக்கலாம். Once the service program got ended, at the end we are mentioning EI so that further interrupts will be allowed now. Clear? Then we are writing the return instruction so that it return to the, it pop the return address saved into the stack to the program counter and it is continuing the main program. Clear? So what is the advantage of interrupt? Then polling. In the case of polling, what CPU do? Last class correct? Polling is a method to service all the IO devices connected with the CPU. Correct? What is the drawback in polling? Who has to check whether the device is required service or not? In the case of polling, the CPU has to check all the IO devices whether it need any service or not. Correct? Whereas in the case of interrupt, yes, very good. It reduces the performance of the CPU. Very good, Anthony Surya. Fine. Polling is an inefficient method. Fine. Okay. Whereas in the case of interrupt, the device which wants some service to be done by the processor, it is initiating the signal. Correct? It is initiating the interrupt. Fine. It is sending the request to the CPU. Fine. Whenever the device wants some service from microprocessor, at that time it has to interrupt the CPU. Fine. In turn, the CPU acknowledge the interrupt, okay, and do the service. The service is done by the ISR routine. The ISR routine, what has to be done to the interrupting device? That is written in the service routine, interrupt service routine. Clear? So this program we call it as interrupt service routine. The starting address of the ISR, okay, that we call it as vector address of the interrupt. Okay, in the interrupt service program it is fixed on the, it is fixed by the vector address. Okay, for each interrupt you will be having a vector address. For interrupt the particular address is generated by the CPU. Okay, that is fixed. We cannot change it. The vector address we cannot change it. Fine. Is it clear for everyone? Is the sequence is clear? Yes or no? Fine, fine, okay. So now we will get into the hardware pins available in 8085. Already we have discussed about this. So totally we are having how many interrupts in 8085? How many interrupts we are having in 8085? Is it 6, Danya? Kindly check and tell. How many hardware interrupts we are having in 8085? 5 interrupts, okay. Trap, RST 7.5, 6.5, 5.5 and INTE. Okay. INTE is a acknowledgement pin. Okay. See in the interrupt processing sequence send interrupt acknowledgement that is done by the pin INTE bar. That is done through the pin through INTE pin bar. Okay, INTE bar. Fine. So this is the signal from CPU to the interrupting device. And the device interrupt signal. Fine. This INTE bar signal is only for INTR. There is a reason behind that. Okay. Is it clear for everyone? See, this INTA bar signal is only for INTR. I will tell you what is the reason behind this later. Okay. As of now, we are having 5 interrupts and 1 interrupt acknowledge pin. Fine. So, as in 8085, we are having only 5 hardware interrupts: trap, RC 7.5, 6.5, 5.5, and INTR. Okay. Now we can classify the interrupt. Okay, so that you can have some idea. Okay, classification of interrupt and its priority. Fine. So, based upon the hardware and software, we can classify the interrupt like this. Okay, hardware means we have physical pins. Okay, in which the input device can be connected so that it can request to the CPU. Fine. So, totally we are having 5 hardware pins. That means 5 hardware interrupts we are having. Fine. Whereas through software also we can generate the interrupt, okay, using the instruction RSTN, correct? RSTN. The N can range from 0 to 7. RSTN. Fine. This is one way of classifying the interrupt, hardware interrupt and software interrupt. The another classification is maskable, non-maskable. See, in this hardware interrupt and the software interrupt, among the hardware and software interrupt, these things are maskable. That means RST 7.5, 6.5, 5.5, INTR are the 4 interrupts we can mask. We can either delay the service to that particular interrupt. The CPU can either delay the service to the particular interrupt or it can be avoided by the CPU. Fine. RST 7.5, 6.5, 5.5, INTR. These 4 hardware interrupts are maskable. That means by writing some program, okay, by writing some program, we can configure the interrupt control of 8085 so that these 4 interrupts can be avoided or it can be delayed to be serviced. Correct? And the interrupt நம்ம என்ன பண்ணலாம்? கொஞ்ச நேரம் வெயிட் பண்ண வைக்கலாம். சர்வீஸ் ஆகாம கொஞ்ச நேரம் வெயிட் பண்ண வைக்கலாம். So that you can continue some important task running in the CPU. Fine? It can be maskable. Whereas the interrupt trap is non-maskable interrupt. This is the only interrupt in 8085 which is non-maskable. Actually, here we mention RST 0 to 7. Okay, these instructions are written by the user only. Fine. If it is needed, we can write it, or else it can be avoided. Correct? Actually, this classification can be done with hardware interrupt especially. Fine. Out of the 5 hardware interrupt, 4 are maskable. The only non-maskable interrupt is trap. Okay, so trap is the only non-maskable interrupt available in 8085 microprocessor. Okay, then based upon the vector address, the interrupt can be classified like this. Okay, except INTR, trap 7.5, RST 7.5, 6.5, 5.5. Okay, then all these software interrupts are having the vector address. Okay, except INTR. The interrupt INTR doesn't have the vector address. Okay, that's why we have a interrupt acknowledge pin. Okay, that's why we have a interrupt acknowledge pin for INTR. அதாவது இந்த இன்டரப்ட்லாம் நமக்கு வந்துச்சுன்னா அதோட அட்ரஸ் ப்ரீடிஃபைன்டா ப்ராசஸருக்கு தெரியும். It will generate the address for the vector interrupts. Okay, so by conclusion we can say based upon hardware and software we are having 2 classification. Fine. So hardware interrupts are trap 7.5, RST 7.5, 6.5, 5.5 and INTR. Then through software also we can create some interrupt that we call it as software interrupt, RST 0 to RST 7. Fine. Then based upon the masking property, okay, the interrupt is classified into maskable and non-maskable. So except trap, all are maskable interrupts. Fine. Coming to the vector or non-vector classification, except INTR, all other interrupt is having vector address. Fine. Is the classification is clear to all of you? Any doubts? Hardware அப்படின்னு சொன்னா meaning என்ன? Physical pins will be there. Okay, fine. Now, so this is the order of priority. Trap is having the highest priority, then 7.5, 6.5, 5.5, then INTR. INTR is having the lowest priority among all the interrupt. Fine. So why we are having priority? Any idea? Have you heard about the word priority in the case of in digital electronics? When you are studying digital electronics, have you heard about the word priority? Any idea? Yes. Yes, very good. Priority encoder. Very good. Okay. So the same thing used here to resolve the priority of the interrupt. Okay. When more than one interrupt simultaneously occur, what the CPU has to do? It has to allow only one device to be serviced. Correct? After finishing the high priority device, high priority interrupt, okay, it can go with the next order priority. Correct? So this is the order of priority in 8085 microprocessor interrupts. Okay. Trap is having the highest priority, then 7.5, 6.5, then 5.5, then finally INTR. Fine. INTR is having the very lowest priority. Clear? Is this thing is clear to all of you? See, when more than one interrupt, say for example, trap and RST 5.5 occur, which will be serviced first? Trap and RST 5.5 if occurred simultaneously, which interrupt will be serviced first? Very good, trap. Okay, fine, fine. Okay. Okay, in the case RST 7.5 and INTR comes, RST 7.5 and INTR comes, which one will be serviced first? Yes, RST 7.5, obviously, very good. Okay. So this priority order is resolved by a circuit called priority resolver. Okay, that technically we call it as interrupt handler. Fine. ஒரு interrupt வந்தா என்னென்ன விஷயம்லாம் நடக்கணும் அதுக்கு உண்டான hardware that we call it as priority handler. Fine. Okay. So இப்போ நம்ம சொன்னோம் இல்லைங்களா இதெல்லாம் process. ஒரு interrupt வந்தா என்னென்ன நடக்கணும்ன்றது it's a process. Okay, to do all those things, that means to resolve the high priority interrupt, when more than one interrupt occurs, to resolve the high priority interrupt, we have a circuit that we call it as interrupt handler. Okay, fine. So vector address of software interrupt and hardware interrupt. So this is the vector address of software interrupt and this is the vector address of hardware interrupt. Here one interrupt is missing in the case of hardware interrupt. Can you people type it in the chat? எந்த hardware interrupt இங்க நம்ம லிஸ்ட் பண்ணல பாருங்க. Trap இருக்கு பாருங்க. Trap is there. Yes, very good Shivakumar. INTR is missed here. Why? Already we told whether INTR is vector interrupt or non-vector interrupt. Yes, it is non-vector. That means it doesn't have any vector address. So non-vector, INTR is non-vector. Fine. Okay, how the address is calculated by the CPU? Actually, there is some internal hardware designed by Intel. Okay, it will generate the vector address. Okay, how it can be calculated is like this. So 8 into RST value in hexadecimal. Okay, say for example, you consider RST 5, vector address of RST 5. So what is the value of RST 5? N value in என்ன வருது பாருங்க 8 into n you can put. Correct? 8 into n. What value you will be getting? 8 into 5. What value you will be getting? In decimal you will be getting what? 8 into 5 எவ்வளவு பார் 40. It has to be converted into hexadecimal. What is the value for that? If it is converted into hexadecimal, what will be the value? Yes, decimal to hexadecimal convert பண்ணீங்கன்னா என்ன கிடைக்கும்? Yes, 28H, correct? But address is always 16 bit, so it will be like 0028H. That's all. Fine. So each vector interrupt is having its unique vector address. Is it clear for everyone? So vector interrupt na புரிஞ்சுதா? What is meant by vector address? Whenever an interrupt occur, okay, there is a predefined address location, there the service program vector into. Fine. That address we call it as vector address. So அந்த இடத்துல தான் நம்ம service program எழுதணும். Okay. Yes, is it clear or not? So this is for our understanding. Vector address எப்படி ஞாபகம் வச்சுக்கலாம் அப்படினு பாத்தீங்கன்னா that number into 8. Okay. Trap is equivalent to RST 4.5. Kindly note down, trap is equivalent to RST 4.5. So trap ஓட vector address என்னன்னு calculate பண்ணி சொல்ல முடியுமா? ஆல்ரெடி அங்க லிஸ்டா இருக்கு. So 4.5 into 8 போட்டீங்கன்னா எவ்வளவு கிடைக்கும்? I think 36 in decimal. Hexadecimal convert பண்ணீங்க அப்படின்னா 24H. That's what listed here, 0024H. Fine. Okay. Fine. See, when we are saying INTR is non-vector, we have some benefit. We have some benefit with INTR interrupt. Okay. What it means, when INTR interrupt occur, there is no vector address for it. Correct? So what the CPU will do? See, in the case of other interrupts, we are having a vector address calculated by the CPU, correct? So this vector address can be calculated by the CPU during the acknowledgement of a particular interrupt. Okay. In the case of INTR, it is non-vector, correct? Even though it is non-vector, we have some benefit over it. Okay. We will discuss about it later. As of now, how the program for INTR can be run, where the program for INTR should be located. It's a questioning, correct? Yes or no? See, in the interrupt la vanda in the particular memory address la program run aidum sollu, correct? No issues. When INTR comes, it's a question mark, correct? How it has to know the address from where it has to execute the program. Fine. Antony Surya type temporary address. It's not like that, Antony Surya. Fine. See, when I am asking you to do something, okay, I have to tell the address, correct? Each vector interrupts are having its unique vector address, whereas in the case of INTR, INTA bar signal is generated. Fine. When INTR interrupt occurs, the INTA bar will get generated. That means interrupt acknowledgement cycle. Okay. The microprocessor will get into interrupt acknowledgement cycle. During this cycle, the interrupting device has to provide the vector address. How it can provide the vector address? Usually the processor fetch the output from memory or input output device. Usually output வந்து எங்க இருந்து fetch பண்ணும் CPU? Yes, any idea? Memory. Okay, so program நம்ம memoryல தான் எழுதிருப்போம். To fetch any instruction from the memory, to fetch any instruction, it has to fetch the output from the memory only. Okay, but in the case of INTR interrupt, it need address. Okay, there only you will be writing your service program. Okay, how you can point to the particular address. Okay, so that can be done in such a way that when the interrupt occur, the microprocessor will send an interrupt acknowledgement cycle, which is nothing but an opcode read from an IO device, or the opcode given by the IO device, which is going to give a pathway from where it has to execute the service program. Okay. Okay, sir. இப்போ எனக்கு address சொல்லணும், கரெக்ட்டா? When the INTR interrupt comes, INTA bar is getting generated. So the INTA bar generate ஆனா நமக்கு என்ன ஆகும்? The interrupting device from which it is going to read the output. That's the meaning for it. Is it clear for everyone? Generally, memory la read பண்ணனும்னா என்ன signal generate ஆகும்? Which signal will get generated? Yes, read bar signal will get generated. Fine. So here, to get the opcode from the IO device, okay, it is generating INTA bar signal. Okay, so INTA bar signal is going to act as a reading the output provided by the IO device. Okay, indirectly it is giving the address. Okay, can you people type it in the chat? Which kind of instruction can give an address to microprocessor? From where it has to execute the program. Generally, ஒரு address உள்ள program execute ஆகும்னா என்ன instruction நம்ம யூஸ் பண்ணோம்? A function is written, an interrupt service routine is written somewhere, okay, or some subroutine is written somewhere. Which instruction you will use to call that particular subroutine? எந்த instruction நம்ம யூஸ் பண்ணுவோம்ப்பா? Yes, very good. Sajesh typed, Anthony Surya typed, very good. Call instruction. Okay, the opcode for call instruction is CD. Okay, CD. The opcode for call instruction is CD. So meaning enna? During the first INTA bar, the device has to give the opcode CD to the microprocessor. Correct? Idoda mudinju pocha. After call, what has to be given? After call, what has to be given in the instruction? See, the instruction is still not complete, Sajesh. I am speaking about the call instruction, correct? See, when the INTR interrupt occurred, during the first interrupt acknowledgement cycle, it read the output CD from the device, correct? With that, it doesn't know from where it has to call the program, from which memory location it has to call the program. It doesn't know, so it has to read the address. So it generates one more INTA cycle. It read the lower byte, correct? Then it will generate one more INTA cycle. It read the higher byte. So 3 INTA cycles are involved if the particular input device is giving a call instruction to the CPU. Fine. By this means only it can tell the address. So by INTR interrupt on the vector address eppadi kedaikum? The interrupting device should give the call instruction. Okay. Yes, is it clear? Okay. Now I want to ask you one question. Okay. Is there any instruction we have? We call it as 1 byte call instruction. Did we call any instruction as 1 byte call instruction? No, Shivakumar, 1 byte call instruction. When I am teaching the instruction itself, I have told you. One byte call instruction. No, return is a instruction to return from the subroutine to main program, correct? What about the function of RSTN? RSTN oda function enna? இந்த instruction execute பண்ணா என்ன ஆகும்? It's a software interrupt. We all know about it. Yes, restart from a vector address, correct? Whether it is equivalent to call or not. Call na பக்கத்துல address கொடுப்போம், கரெக்ட்டா? இங்க number கொடுத்துப்போம். That's all. Fine. So you have to know one thing. The device which is interrupting the microprocessor has to give an instruction so that it can know the address. It can be given either like call address, correct? Or else it can send the opcode of RSTN instruction. Say for example RST5 அப்படின்னு சொன்னோம்னா அதுக்கு opcode EF. The opcode for RST5 is EF. So this is the opcode for RST5. I have typed in the chat. Okay. Meaning enna? The interrupting device has to send the byte, first byte. எனக்கு EF னு கொடுத்துச்சுனா meaning enna? Further INTA bar cycle will not be generated. Suppose if it give the opcode as CD அப்படின்ற byte send பண்ணா மட்டும்தான் 2 more INTA cycle will happen. Fine. So for INTA bar purpose புரிஞ்சுதா? The interrupt acknowledgement signal is used to read the instruction given by the IO device during interrupt acknowledgement. Fine. When an interrupt is occurred in a microprocessor through INTR pin, that's very, very important. It's not for any other interrupt. All other interrupt is having vector address except INTR, correct? When INTR interrupt occurred, The interrupting device will send the first byte either CD or EF. EF in the case RST5. RST0 na adukku vera opcode irukku. For example, I am telling RST5. EF is the opcode for RST5 instruction. So from where the program will run? Here you can see in the presentation. RST5 would vector address 0028H. Correct? So from memory address 0028H, it will start running the program. That's all. Is it clear for all of you? Sir, non-vector interrupting சொன்னா நமக்கு என்ன பண்ணும்? Interrupting device da vector address கொடுக்குது. Correct? Fine. Okay. In module 2, you will be having 8259 அப்படினு interrupt controller. Okay, programmable interrupt controller we are having 8259. Okay. So when we are studying about 8259, you can know the advantage of INTR interrupt. Okay. Generally, INTR interrupt is used to expand the number of interrupts. Okay. See, 85 la total of 5 hardware interrupts only available. Fine. To increase the number of interrupts handled by 8085, in assistant, it can use the 8259 IC. Okay. A single 8259 IC can capable of handle 8 interrupts. Correct? So that particular thing will be connected to INTR. So that and all you will learn later when you are studying 8259. Okay. As of now, we must know what happened when interrupt occurred in INTR pin. When interrupt occurred in INTR pin, the acknowledgement signal INTA bar. Okay. During the first INTA cycle, interrupt acknowledgement cycle, it read 1 byte given by the device. Okay. If it is CD, it needs 2 more INTA bar cycle. Correct? 2 more interrupt acknowledgement cycle. Okay. If it is the opcode of any RSTN instruction, with that itself it know the vector address. That's all. By that means only the input device can tell the address. Okay. தப்பா புரிஞ்சிக்க கூடாது. INTR interrupt வந்தா address தான் என்னோட device கொடுக்குமா கிடையாது. Indirectly it is providing the vector address only. Okay. Indirectly it is providing the address only, but in terms of call instruction or RSTN instruction, it is giving the vector address. Sorry, it is giving the address. It is not vector address. Okay. Fine. We'll move next slide. We will move into the next slide. So this is the entire structure of the 8085 interrupt hardware. Okay. Please kindly take a screenshot of this image. Okay. So in the particular circuit on the screenshot எடுத்துக்கோ. Fine. We'll go one by one. Okay. So column the பிரிச்சிருக்காங்க. Priority. Fine. Then which type of input the interrupt is sensed. Fine. Then what about the hardware pins available for each interrupt? Fine. So among the 5 interrupt, trap is having the highest priority. Correct? The trap interrupt is having the highest priority. So priority 1, it is marked with priority 1. Fine. Then we have RST 7.5. Okay, priority 2. Then RST 6.5, priority 3. Then RST 5.5, priority 4. Then finally INTR priority 5. Fine. This is the first thing we have to know. Priority of the interrupt. Fine. Then which type of sensing can be done by the interrupt pins? Okay, each interrupt pins are divided into many types. Okay, based upon the sensing of the interrupt. That means when an interrupt occurs, say for example, normally a signal can be high, okay, or low at any point of time. When interrupt occurs, RST 7.5, 6.5, sorry, RST 6.5, 5.5, INTR. These 3 interrupts are level sensitive interrupt. That means in the interrupt recognize it has to hold the interrupt pin high till it is being serviced. Service nadakara varaikum the pin edhula maintain agum. It has to maintain in high logic. That means level 1 it is sensing. Correct? The interrupt RST 6.5, 5.5 and INTR are level sensitive interrupt. What about RST 7.5? You can see the image and tell. You can see this part and tell. What about RST 7.5? Whether it is level sensitive or edge sensitive? Yes, very good. It is edge sensitive, positive edge. Whenever the signal transition from 0 to 1, the interrupt will be recognized. Fine. As it is edge sensitive, definitely it need a flip flop to store the request. So இங்க ஒரு flip flop இருக்கு இல்லீங்களா, இது பேர் வந்து RST 7.5 flip flop இது பேர். Fine. Whenever an interrupt occurred, this flip flop will get set. நல்லா புரிஞ்சுக்கணும். Whenever an interrupt occurred at 7.5, RST 7.5, this RST 7.5 flip flop will get set. Correct? That means the interrupt request is stored. That's the meaning for that. Whereas in the case of 6.5, 5.5 and INTR, we doesn't have any flip flop like that. Okay, edge sensitive அப்படின்னு சொன்னா கண்டிப்பா என்ன ஆகணும்? It has to be stored. Whenever an edge occurred, at that time, logic 1 is written into this particular flip flop. That's all. Clear? Is it clear? Edge sensitive அப்படின்னு சொன்னோம்னா கண்டிப்பா அதுக்கு என்ன இருக்கணும்? It has to be needed a flip flop so that the request can be stored. Whenever the processor check for this particular interrupt, it will check the status of this flip flop first. RST 7.5 flip flop check பண்ணி பார்க்கும். இது 1 இருந்துச்சுன்னா மீனிங் என்ன? ஏதோ ஒரு டைம்ல நமக்கு interrupt வந்து occur ஆயிருக்கு. Fine? Okay. Now coming to the trap. Trap எங்க இருக்கு பாருங்க? Here. What about the sensitivity of the trap interrupt? You can see the picture and tell. What about the nature of trap interrupt? Whether it is edge sensitive or level sensitive. You can see the picture and tell. Both things are marked there. What it means? Both edge and level sensitive. Trap interrupt is both edge and level sensitive. Correct? Is it clear? Both edge and level. Clear? So this is the high priority interrupt. It is having the sensitivity both level as well as edge. Okay. Whereas in the case of RST 7.5, it is only edge sensitive. Whereas in the case of trap, it is both edge and level sensitive. Okay. Why it is like this? Why it is like this? Any idea? Any idea? It is having the very highest priority. There is no doubt in that. Then why it is both edge and level sensitive? Okay, we can discuss about it later. We will go into the next things. Fine? Fine. The next thing is mask bits. Clearly you can see there is one bit available here. This we call it as M7.5. Here it is not mentioned. Kindly note down. It is M7.5, M6.5, M5.5 Whenever this particular bit is 1, the corresponding interrupt get masked. That's why these interrupts are called maskable interrupt. RST 7.5, 6.5, 5.5 are having individual mask bits. Okay, are having individual mask bits. That's why this interrupt RST 7.5, 6.5, 5.5 are maskable. Is there any other interrupt is maskable? 7.5, 6.5, 5.5 mattumda maskable interrupt. Is any other interrupt is maskable? Yes, very good, Anthony Surya. INTR is also maskable. Okay, let me know now. Let me discuss now. Okay, is the presentation slide is visible clearly for all of you? Yes. Can you type it in the chat? Full screen la theriyudha parunga. Yes. Okay. Fine. So RST 7.5 ku inge mask bit M 7.5, 6.5, 5.5 is there. Fine. Here you have one more flip flop. Here you can see one more flip flop. Interrupt enable flip flop. Whenever you write the instruction EI, it is a SR flip flop. Fine. In the EI instruction execute agra time la enakku enna agum? This flip flop will get set. In the flip flop enakku set aayirundha irrespective of the mask bit, all other interrupts will be enabled except trap. Alla gavanichinga theriyum. Here we have one circuit. 3 input and gate. One of the input from the mask bit is bubble. That invert panni kudukum. That means alla gavaninga RST 7.5 interrupt occur ஆனிச்சுனா இந்த flip flopல 1 இருக்கும். The first input is 1. Okay, the second input is from mask bit. Mask bit எனக்கு 1 இருந்தாலே இங்க என்ன input கிடைக்கும்? 0. That means the output becomes 0. This interrupt will be masked. Is it clear? Are you able to understand what I am saying? Individually mask பண்றதுக்கு இந்த 3 bit இருக்கு. RST 7.5, 6.5, 5.5. But globally எனக்கு enable or disable பண்றதுக்கு we have interrupt enable flip flop. At what condition this flip flop will get set? Can you people type it in the chat? When interrupt enable flip flop will get set? Whenever the CPU executes EA instruction, correct? That is the only way to enable this particular flip flop. அப்ப இந்த flip flop நான் reset பண்ணியிருந்தா என்ன ஆகும்? If I execute the DA instruction, fine, what will happen? This interrupt enable flip flop will be disabled, correct? DA instruction execute ஆனாலோ இல்ல reset பண்ணாலோ இல்ல any interrupt recognize ஆனாலோ எனக்கு என்ன ஆகும்? EI flip flop will get automatically reset. Is it clear for all of you? Is it clear for all of you? இந்த flip flop set ஆகிறதுக்கு ஒரே ஒரு possible condition, execution of EA instruction. What are the other possible for resetting this interrupt enable flip flop? Either by executing DA instruction or processor reset பண்ணாலும் இந்த flip flop reset ஆயிடும், or any interrupt recognize. ஏதோ ஒரு interrupt recognize ஆனிச்சுனா நான் சொன்னேன் இல்லீங்களா, further interrupt will be disabled. Automatically the flip flop வந்து disable ஆயிடும், reset ஆயிடும். Clear? If this particular flip flop is reset, INTR, RST 7.5, 6.5, 5.5, all the 4 interrupts will get masked. That's why INTR is also comes under maskable interrupt. Clear? Can I have a question now? How you can mask INTR interrupt? How you can mask the INTR interrupt? By which way you can mask the INTR interrupt? INTR interrupt mask பண்ணனும் அப்படினா what we have to do? You can see INTR interrupt நமக்கு 1 இருந்தாலும் இந்த flip flopல 1 இருந்தாதான் this particular thing will happen. Is it clear or not? See, ஒரு விஷயம் நல்லா புரிஞ்சுக்கோங்கப்பா. 7.5, 6.5, 5.5லாம் இண்டிவிஜுவலா மாஸ்க் பிட் இருக்கு, பிளஸ் interrupt enable flip flop அதையும் டிபெண்ட் பண்ணி தான் இருக்கு. Clear? What about INTR? INTR we don't have any mask bit. Okay, this INTR depends only on the interrupt enable flip flop. If you reset this particular interrupt enable flip flop, INTR, RST 7.5, 6.5, 5.5 all will get masked irrespective of the mask bit. Is it clear for everyone? Yes? Yes or no? Yes or no? Yes, fine. Only very few are typing. Okay. See, priority முடிஞ்சது. Sensitivity of the interrupt is over. Okay. Hardware pins, we know the naming for the particular interrupts. Okay. RST 7.5 is having RST 7.5 flip flop. Whenever interrupt occurred through RST 7.5, this flip flop will get automatically set. Fine. When this flip flop will get reset அப்படின்னு பார்த்தோம்னா either by reset or RST 7.5 interrupt recognize ஆகலாம். அந்த ரெண்டு கண்டிஷன்ல தான் இது ரீசெட் ஆகும். Fine. Whereas EI flip flop will get reset either by DA instruction execution or by reset operation if any interrupt got recognized. At that time, interrupt enabled flip flop will also get reset. Fine. Once it comes across all the things, okay, the interrupt will be allowed. Fine. To enable all the interrupt, what we have to do first? Can you people type it in the chat? To enable all the interrupt, first step what we have to do? First step what we have to do? இந்த எல்லா இன்டரப்டும் ப்ரோக்ராமிங்ல எனேபிள் பண்ணனும்னா என்ன பண்ணனும்? Which instruction we have to use to enable all interrupts? Yes, EA instruction execute பண்ணனும். By executing EA instruction. அது மட்டும் எக்ஸிக்யூட் பண்ணா போதுமா? EA instruction execute பண்ணா EA flip flop set ஆயிடும். அது மட்டும் போதுமா? What must be the status of the mask bit? Mask bit எனக்கு 1 இருந்தா masking ஆயிடும். 0 இருந்தா தான் எனக்கு என்ன ஆகும்? unmask ஆயிருக்கு கரெக்டா? Is it clear or not? By executing EA instruction, you can enable INTR interrupt, whereas the other interrupts still depend on mask bit. Correct? Yes or no? Yes or no? What about trap? Whether trap is having any control to mask now? Trap oda line பாருங்க ஸ்ட்ரைட்டா போகுது வெக்டர் அட்ரஸ்க்கு நேரா போயிடும். Is it clear? Yes, the other interrupts can be maskable. Fine? Okay sir, INTR interrupt வந்தா நம்ம என்ன சொன்னோம்? Get RST code from external hardware. நம்ம CD ன்னு சொன்னது இன்னொரு எக்ஸாம்பிள் கரெக்ட்டா? Or else it will get the opcode for RSTN instruction. RST0 வந்தா இந்த அட்ரஸ்க்கு போயிடும் 0000. RST1 வந்தா 0008. Like that it will vector into the particular address. That's all. Okay, that's all about the interrupt structure of 8085 microprocessor. Fine? Is it clear? See, as RST 7.5 is edge sensitive, we are having a flip-flop. Okay, but we don't have a flip-flop here in trap because we no need to store the interrupt request in the case of trap as it is the high priority interrupt. Whenever trap occurs, it has to be service, correct? So that's the reason. Fine. The other thing why it is both level and edge sensitive means to trigger the interrupt. எனக்கு interrupt enable ஆகிறதுக்கு எனக்கு என்ன ஆகணும் அப்படின்னு பாத்தீங்கன்னா it has to change from 0 to 1 and it has to maintain high. Clear? But trap interrupt keep on நம்ம high பண்ணிட்டே இருந்தா again and again இது சர்வீஸ் ஆகுமா? கிடையாது. Definitely no. Even though trap we say both level and edge sensitive, okay, எனக்கு level maintain ஆயிட்டே இருந்தா மட்டும் சர்வீஸ் ஆயிடுமா? கிடையாது. Fine. Initially it has to come from 0 to 1, then it has to maintain high. Fine. Why it is designed like that? Otherwise the trap interrupt will keep on getting serviced. Okay, and the trap interrupt நம்ம hold பண்ணிட்டே இருந்தா அந்த சர்வீஸ் ப்ரோக்ராமே ரன் ஆயிட்டே இருக்கும். Otherwise it sends the edge. That's why it is both edge and level sensitive. First edge sense ஆகணும், அதுக்கப்புறம் level maintain ஆயிட்டே இருக்கும். That's it. If it keep on high, once it is serviced, again இது வந்து service ஆகாது. Clear? Fine. So this is the way to mask the interrupt. RST 7.5 mask பண்ணனும்னா என்ன பண்ணலாம் பாருங்க. Either you can set this mask bits RST 7.5, 6.5, 5.5. The mask bit set பண்ணிட்டீங்கன்னா you will be having zero logic here. கரெக்ட்டா? Mask bit நான் 1 ன்னு போட்டா இங்க போற input என்ன ஆகும்? The AND gate inverting input தான் போகுது. Correct? So it becomes 0. So all the interrupt will get masked if the corresponding bits are set. Fine? Okay. Or else mask bit la நம்ம 0 பண்ணிருந்தாலும் interrupt enable flip flop if it is 0, what will happen? All interrupt will get masked. Fine? So we have to know how this bits can be set or reset. Okay, how this particular mask bits can be set or reset. இது எப்படி பண்றது அப்படின்றது we will go with it. Fine? So kindly note down this slide. So this is the masking methods of all the interrupt. RST 7.5 mask பண்ணனும்னா either you can reset the interrupt enable flip flop or you can mask RST 7.5 bit, or else you can reset RST 7.5 bit. Clear? எது வேணா பண்ணலாம். Clear? When RST 7.5 flip flop will get reset? Reset operation or any, sorry, or 7.5 should be recognized. Once RST 7.5 interrupt got recognized, automatically this bit will get clear. அதான் previous இதுல பார்த்தோம். So in the flip flop reset ஆகிறதுக்கு என்ன condition? Either reset operation or RST 7.5 interrupt acknowledge ஆயிருந்தா போதும், recognize ஆயிருந்தா போதும். That's all. Okay. So this is the way or the method we can able to mask the interrupts. Okay. So the trap மட்டும் வரவே வராது. That's why it is called as non-maskable interrupt. Fine. So we can conclude all the interrupt and its properties with this table. Kindly take a screenshot. So interrupt name இங்க கொடுத்திருக்கிறோம். Fine. INTR, RST 5.5, 6.5, 7.5 trap. Correct? So இதுல எது எதெல்லாம் maskable பாருங்க. INTR, RST 5.5, 6.5, Okay, RST 7.5. Except trap. Trap is the only non-maskable interrupt. Okay. Then masking method. Every mask panla abin sono. EIDA is the only possible way to mask or unmask INTR interrupt. Fine. What about in the case of RST 5.5, 6.5, 7.5? EIDA illama, we can have one instruction called SIM. Okay, that we will discuss in the next session. SIM instruction we can use. The instruction SIM, set interrupt mask. So this instruction can be used to mask RST 7.5, 6.5 and 7.5 interrupt. So otherwise we mask pannalam, or else by disabling the interrupt we can mask. Fine. Then INTR is non-vector, so no vector address. All other interrupt is having vector address. Okay. Fine. In the case of interrupt request storage, only RST 7.5 is having the flip-flop. Okay, only RST 7.5 is having the flip-flop. So it is having the property of storing the interrupt. What about the other thing? It is not storing the interrupt request. Okay, interrupt request is stored only in the case of RST 7.5. Okay, then triggering method, when it will get sense, level sense, INTR, RST 5.5, 6.5 and all. Okay, RST 7.5 is edge sensitive and the trap is both level and edge sensitive. Both level and edge sensitive. Fine, both edge and level sensitive. So with this we will stop today's session. Okay. By next class, we will continue with SIM and RIM instruction. Okay, so that we can know how to mask the interrupt. Fine. So now I am going to stop the presentation.